All right, welcome back to the AI Research Roundup. I am Alex. So today we're looking at multi-head temporal latent attention, a paper from May 19th, 2025, trending on Papers with Code. It tackles the large memory footprint of the key value cache, or KV cache, that's temporary storage in transformer models used for efficient inference. The core idea here is multi-head temporal latent attention, or MTLA, which further compresses this key value cache along the temporal dimension. This method uses what's called a hypernetwork, basically a small helper network, to dynamically merge older cache entries. This promises big speedups and memory savings compared to standard multi-head attention, or MHA, while maintaining quality. And if you want to dive deeper, the authors have made the code for this work available. So, on their GitHub, you'll find the Multi-head Temporal Latent Attention Python module, and also a full open-source toolkit for end-to-end speech and language processing, complete with experiments and setup recipes. Okay, so here really helps visualize the core idea. It contrasts the standard multi-head attention, which we've called MHA on the left, with the proposed multi-head temporal latent attention, or MTLA, on the right. In the standard MHA, you can see the attention input directly populates a full multi-head key value cache over time. The multi-head queries then attend to this entire cache. But with MTLA, the attention input is first processed into what are called low-rank latent vectors. These vectors then form a compressed temporal latent key value cache, which is updated. This compressed version is what the multi-head queries use, leading to that memory saving we talked about. Okay, so dives deeper into the nuts and bolts of multi-head temporal latent attention, showing both the inference and training stages. Part A details inference, where attention inputs are processed incrementally, and the model attends to a temporary compressed key value cache that's dynamically updated. Part B just highlights that a simple key value downsampling approach would mismatch this process. Then, Part C shows the crucial training step. It uses what's called a stride-aware causal mask. A causal mask, generally, prevents the model from seeing future information during training. This stride-aware version is tailored to match the specific strided compression happening during multi-head temporal latent attention inference. So now that we've seen how multi-head temporal latent attention works during inference and training, gives us some concrete numbers. This table shows results on the must-see English to German test set. It compares our new multi-head temporal latent attention against standard multi-head attention and another approach called MLA. We're looking at BLEU scores, which measure translation quality, along with inference time, speedup, and GPU memory. So these figures really highlight the practical benefits of the multi-head temporal latent attention approach. So as those numbers demonstrate, multi-head temporal latent attention really delivers. It achieves impressive reductions in memory and computational demands without sacrificing and sometimes even improving translation quality. This is super important for things like streaming automatic speech recognition, enabling models to handle much longer audio inputs efficiently. Well, that's all for this AI Research Roundup. Thanks for listening. I'm Alex, and I'll see you next time.